The Sun is the star nearest to us. It fuels life, moves winds, generates rain. Inside it, nuclear fusion reactions take place, freeing an enormous quantity of energy. Every day, the Earth receives from the Sun an uninterrupted flow of energy, equal to 15,000 times the world energy consumption. The Sun's importance was perceived by man millions of years ago, and for many cultures, this natural symbol became a god. All around the world, there are monuments that testify the worship of the Sun. The Edfu Temple in Egypt, Stonehenge's stone megaliths in England, the Teotihuacan Temple in Mexico, the Nazca Lines, the Konark Temple in India. 2.5 billion years ago, some groups of water organisms started to produce autonomously the nourishing substances necessary for their life, exploiting the Sun's energy. Since then, plants release oxygen in the atmosphere and produce the majority of the Earth's biomass. This biological miracle is made possible by a complex of chemical and physical reactions called photosynthesis. Nature has always transformed solar energy in chemical energy. However, man has only recently learned how to transform light in electricity. The photovoltaic effect was observed for the first time in 1839 by Alexandre Edmond Becquerel, and its physical aspect was explained in 1905 by Albert Einstein, who received a Nobel Prize for this result. The first solar cell was realized in 1954 in the Bell Laboratories. It was a very expensive technology, which was only used in specific fields, for example for powering artificial satellites. Currently, photovoltaic technology is based on silicon crystals. Silicon is one of the most abundant elements on the planet. It can be found in sand, clay, and rocks. Industrial uses of silicon are not limited to photovoltaic cells. Glass, for example, is made primarily of silicon, as are the electronic components of computers. Today's photovoltaic cells are thin slices of silicon, about 0.5 millimeter thick, covered by metal connections and glass. A silicon-based photovoltaic plant works on average for about 30 years, and it can reach an efficiency level equal to 20%. That is, it transforms 1/5 of the light it receives in employable energy. However, its realization presents various problems. The silicon slices are very fragile and need heavy and cumbersome protective structures. Moreover, the process to obtain silicon crystals is very expensive, since it requires a lot of energy and complex industrial processes. In order to overcome the limits of traditional cells, today science is looking for new solutions by experimenting on alternative materials. The most promising applications use organic conducting materials. These plastic materials are obtained from oil, but they distinguish themselves from common plastic in their ability to conduct electricity, like silicon and metals. Professor Alan Heeger, who won the Nobel Prize for Chemistry in 2000, is among the main actors in this important research. Heeger has managed to obtain photovoltaic plastic cells with a 5% efficiency. Although they are currently less efficient than silicon cells, Heeger's innovative solutions have various advantages. They are economical, versatile, light, and flexible. Heeger cells are formed by a plastic matrix made of semiconductor organic chains linked to a fullerene molecule. The spherical structure, composed of 60 atoms of carbon, discovered by Nobel Prizes Harold Kroto and Richard Spanley. In these cells, when light hits the semiconductor molecule, its electrons are excited and move towards the fullerene. Electrons jump from one fullerene to the other, and finally they are collected by the thin metal layer that is at the base of the plastic matrix. The future applications of these solar cells are very interesting. Flexibility and low prices will guarantee their use on wide surfaces, such as roofs and building facades. While, thanks to their lightness, plastic cells will be able to power all portable electric devices. A valid alternative to plastic materials is represented by inorganic cadmium-based crystals. The pioneer in this field is Professor Paul Alivisatos. In these solar cells, minuscule crystals of cadmium selenide are coupled with cadmium telluride crystals. Light promotes a shift of electrons from the first to the second species of crystals. Electrons are then gathered by the metallic prop at the base of the structure. Like organic cells, Alivisatos' cells are economical, versatile, and flexible. The sun will have an increasingly important role in the future of our planet's energy, and Heger's and Alivisatos' research will offer to humanity a new way to obtain clean energy and a new noble destiny to oil and its derivatives.